If you're looking for a way to measure the speeds of moving objects, the Speed Demon is an easy-to-use, inexpensive, and portable option. To use the device, first I hit the button on the far right to turn it on. Then I hit the button in the middle to cycle through different modes. I hit the button twice to get to the mode that will measure the speed of moving objects in centimeters per second. For my first experiment, I wanted to measure the speed of a car down a ramp, so I set up 3 ramps of varying heights with objects that I found around the house. To measure the speed of the car, I pointed the sensors at it as it went down the ramp. For the ramp with the least incline, I got a measurement of 36.58 centimeters per second. On the ramp with a higher incline, I got a faster measurement, recording the car's speed to be 77.18 centimeters per second. On the ramp with the highest incline, I recorded a speed of 126.26 centimeters per second. From these experiments, I was able to conclude that a larger ramp angle would yield greater acceleration, making the car go faster down the ramp. For my next experiment, I wanted to measure the speeds of a falling object, so I used a ruler and a pencil to make marks on my wall at 20 centimeters, 40 centimeters, 60 centimeters, and 80 centimeters. For each time that I dropped the object, I made sure to line up the middle of the 2 sensors on the back of the Speed Demon with my bottom line at 20 centimeters and to line up the object at the height that I wanted to drop it from. I then dropped the object from 20 centimeters, 40 centimeters, and 60 centimeters above my original 20 centimeter line. Afterwards, I used a piece of graph paper to record the 3 speeds that I measured when dropping the falling object from the 3 different heights of 0.2 meters, 0.4 meters, and 0.6 meters. I used the conversion that there are 100 centimeters in 1 meter in order to convert my recordings for speed into meters per second to make my calculations easier. I decided to plot my points on a graph to see what it would look like. I put height on the x-axis and speed on the y-axis. After plotting my 3 points and looking at the graph that was formed, I saw that it would be in the shape of a parabola, going through the origin at 0, 0 and extending upwards, concave down. It would look something like this. Finally, I wanted to do some calculations with the data I collected from my drop from 0.2 meters. Since the final velocity was 1.84 meters per second, and we were assuming acceleration is constant on this fall, the average velocity would be the final velocity plus the initial velocity over 2, which would end up being 0.92 meters per second. To find the amount of time that it took for the object to fall, I used the equation distance equals velocity times time. I divided each side by velocity to isolate time, and I got time equals distance over velocity. When I plug in my values for distance and velocity, I get a time of about 0.217 seconds for the fall. For the final step of my calculation, I used the equation distance equals 1/2 gt squared. To manipulate the equation, I first multiplied each side by 2 to get rid of the 1/2. After I did that, I ended up having to divide each side by t squared so that I could get g, or gravity, alone. Once I did that, I got g equals 2d over t squared. For my very last step, I plugged in my numbers to get an approximation for the acceleration due to gravity. While I did not get the exact value of 9.8 meters per second squared, I came very close with an estimate of about 8.49 meters per second squared. It makes sense that we are a little bit off of the actual value here, as we did not account for air resistance, and there is probably some human error in that we cannot hold the device at exactly the height we accounted for in our calculations. Using only things that you could find around the house, I was able to use the Speed Demon to measure the speeds of moving and falling objects, make a graph, and do some basic calculations. So, get creative and see what you can do with the Speed Demon.